We'll talk about Lagrangian topologies in tropical hypersurfaces.
So thank you very much for the invitation. It's a great honor to speak here. And my main point of the talk would be to advocate for this object, which is called phase tropical varieties. I'll be talking about hypersurfaces. It's a combinatorial object, which is kind of very computationally useful if you want to do any kind of mirror symmetry, for instance. So let me start with the basic data. So we have a lattice, n-dimensional lattice, n. We have linear functions, integral linear functions on this lattice, m. And we also be using sometimes affine functions. And we are given a finite set of points in that lattice. Maybe I'll draw an example. I'll draw it in a second. And Q is a convex hull of those functions. That's going to be our polytope, our Newton polytope for the hypersurface. And we also need a convex function eta, which, if you look at its upper graph, then if you look downstairs, then you see that it defines a triangulation of Q. All right, that's the initial data. So given such a set of monomials A, we could look at a generic complex hypersurface, affine hypersurface, for where CAs are essentially like any coefficients outside the discriminant. So we don't want any singularities, and also it should behave nicely at the boundary of the toric compactification. So the thing we proved with Gabe Kerr is that this thing is actually homeomorphic to a phase tropical hypersurface. So I didn't define the phase tropical hypersurface yet. I'm going to do it in the next slide. Okay. Here is the definition. So we start, first of all, with a tropical hypersurface. This is, if you just look at your polynomial and write it as a, in a tropical form, where you replace all the pluses by maxes, by maximums, and all the products by the pluses, then you get a real piecewise linear convex function, namely this one. And you look at, so it bends somewhere, and this is the corner locus. If you look at this corner locus, this is the tropical hypersurface. In the story, there is this order reversing bijection between the faces of the tropical hypersurfaces and the faces of your triangulation. I'll give an example in a second. So this is a usual tropical hypersurface. We're going to enhance it by putting some fibers over the strata of those tropical hypersurfaces. The strata are going to be the co-amoebas. So we have amoebas, which is the image of the log map of the usual complex hypersurface, and we have a co-amoeba, which is the image of the argument map. So just look at the arguments of your variables and see what's the images in a torus. So if you have a stratum, say tau, then we have a corresponding face of h eta, and over that face h eta we put this co-amoeba as a fiber. And we put it all together. That defines, well, at least a topological space, which is called a phase tropical hypersurface. So I think this is actually a complicated space. If you think of it, it is. So for the curves, though, it is very simple for the curve, and it's sort of very obvious that it is homeomorphic to the usual complex curve. But if you go to the next, so this example doesn't show how complicated it is, but if you try to do it for the surfaces, then you see that the fibers over vertices, for instance, are going to be three-dimensional things, and sort of they glue together in a very, very complicated combinatorial object, and it's sort of it was an open conjecture of Viro actually that this is even a manifold. So, but so we proved with care that this is not only a manifold; it's actually homeomorphic to the original complex. So this is an example, a simple example, deceivingly simple in some sense. The curves where everything is sort of obvious. So this is my set A. I look at the points, the origin, the 2, 0, 1, 1, 0, and 1 is 2, 3. That's this point 2, 3. And the function I chose, eta, is 0, 0, 0 everywhere except at this point 1. So in some sense, you think of it as sort of a bending along this edge, this PL function. So this is a tropical curve, which is obviously dual. I'm not sure if you see all the colors here, but the colors correspond like this, supposed to be like a vertex here. This edge corresponds to this edge here, and so forth. And this edge corresponds to this compact edge over here. So, all right, so what do we put on every strata here? So that's my picture for the next slide. So, okay, this is our curve. So over the rays, the coamoeba, well, if you look the ray or the interval, that corresponds to the interval in a triangulation. So it's only two monomials. If you set one monomial plus another monomial equal to 0, the fiber is actually going to be a torus. So in this case, this is going to be a circle. The fibers over the vertices are the most complicated ones. So this is the fiber over vertex. This is like twice the fiber. Well, I mean, it's 2 times the torus. So the actual fiber consists of only 2 triangles here. The parallelogram in the middle? Where is the parallelogram?
I mean, like the corner. Or okay, so I mean, these are happening in tori. So what's the fundamental domain for the?
This is from minus. Okay, so this is the origin, and this is 2 pi. Okay. So this is like from minus 2 pi to 2 pi. So it's twice the fundamental. 4 times in this case. Okay. Yeah. And same thing is here. But what you see here that this is, if you go back to this, this is a non-unimodular simplex. So we actually have so for this simplex we have a normal pair of pens, and for this one we have I think this is a volume 4, so we have a 4-to-1 cover of the pair of pens. So this is not unimodular. So I think there are too many. I think this is again 2 times 2 many as there should be. Okay. Okay, so what's the point of this to notice about this coamoeba? That this is actually a complement of the zonotope. In this case, this is a hexagon, and well, for curves it's always a hexagon. It's a complement of this wonderful thing called the zonotope. It's a zonotope of n+1 vectors. Okay, any questions? Phase tropical variety? Very simple thing.
What's the color supposed to mean?
The color is supposed to mean
just for visibility.
I think the blue ones are they like light blue and a dark blue. I think they correspond to this blue here, but one is darker than just for visibility. Okay. Maybe I'll draw a picture for the pair of pens just to get going. So this is a usual pair of pens, a complex one. And if you do the tropical ones, it's going to be fibered over this thing, and the fibration is, so here you have a cylinder. Here you have a cylinder. Here you have a cylinder. And over here you have this thing, this is a fundamental domain of the torus from 0 to 2 pi. The picture would be. And these three cylinders, one glues like this, one glues like this to the circle, and the third one glues like a diagonal circle here. Oh, and obviously, sort of, if you put this thing together, then you get the cylinder. Then you have this triangle over here. Then you have triangle, downstairs, another triangle. So this is apparently homeomorphic to the usual pair of pens. But as I said, this is deceivingly simple. It's much more complicated once you go beyond the curves. Okay. In this object, I'm going to define certain subsets which are supposed to be Lagrangian. So, okay, under this homeomorphism, what we can do now, we can sort of pull back all the structures from the complex hypersurface to the phase tropical one. For instance, we have a symplectic structure. We can study Floer theory or whatever Fukaya categories. We can see what kind of objects we can get on this combinatorial phase tropical thing. So my objects are going to be the pairs. So I start with a simplex tau, and also I need. Okay, this is going to be my basic example for today. Not the one which I gave for the picture, this is too complicated, but this is going to be my convex polytope with triangulated like this. So the curve would be something like this. So if this is tau, the star of tau is all the simplices which are incident, which contain tau. So this is the star of tau. These two simplices and the tau itself. And we need a function on the vertices of the star. So let me take, for instance, 0, 0, 0, maybe like 3 here. This is an example here. And as I said, so it is defined modular the linear, modular affine functions on this thing. So I can, for instance, modify it by adding any linear function. For the unimodular simplex tau, I can always take it to be 0 on tau. But if tau is not unimodular, then it actually has this function has some information about where, in this fundamental domain of the coamoeba are we. All right, so these are the objects. As I said, so I'm going to describe the actual geometric object to this pair. It's going to be a sphere. It's going to be an immersed sphere for the tau in the interior, and it's going to be a ball when tau is on a boundary. So for this tau, maybe I'll briefly say what the sphere is going to be. So question? Q is a convex hull. Q is the whole thing. So this is my Q. In this case, Q is the same as a star of tau. So the sphere is going to be, so for this tau, the sphere is going to lie over the corresponding edge here. So it's going to be a circle, which roughly, if I draw it, I couldn't find any trees here. There are only palms, but so the sphere is going to lie something, so it's going to be, then it's going to be a little twisted over the edge as you go, and then it's sort of like this. That's the object. This is sort of, think of it as a, if it's untwisted, then this is just goes, you know, around this edge, kind of along this edge. And if the tau would be this edge, then this is not going to be a sphere. This is going to be a ball. Well, in this case, like a real line lying over this infinite leg here. And then when I do the homes, of course, I need to do this wrapping thing for the infinite ones. Okay. So this is a precise description how I build the sphere. So, okay, so let me go back to this example. So star of tau minus tau, in this case, is going to be the following picture. So minus is like a Minkowski minus, or plus the minus tau, if you want. This is a star of tau minus tau. That's what it looks like. So it has a, well, you know, the origin, if I take the x minus x, this is going to be the origin. If I have a value, if I have a PL function on star of tau, that actually defines for me a PL function on star of tau minus tau by this formula. This is well defined. You can check. So it doesn't matter how I represent my point in a star of tau as a difference. This is over the same value. So in this case, it's going to be 0, 0, 0, 0, 0, 3, 3. In the same manner, I can do the same thing for the other function eta, which defines for me the triangulation. But for lambda, I actually modify my lambda. So I replace this 0 by 1/2.
What is the meaning of lambda? So you can add a cross construction. What was
lambda is a, so for, my objects are the pairs tau, comma lambda, where lambda is a function on a star of tau, on the vertices of the star of tau. So for every pair, I'm constructing an object. The meaning of lambda is sort of this twisting. So if lambda is 0, then so lambda is 0, I would get like a usual sort of like the untwisted thing. But when lambda is not 0, I do my circle here and twist it as I go along the corresponding edge. Okay, this is some non-necessarily convex function. So how, well, okay, so adding 1/2 is the same thing as just subtracting minus 1/2 from everywhere. Maybe this, so it's 0 here, minus 1/2. So 2.5, 2.5 here. And then I'm constructing this sort of twisted polytope thing. I'll come to that to the next slide. So, okay. So what I'm doing now, this is a PL function on this on the thing, but I can extend it to the PL function on the entire R2 just by going over there, and then I smooth it. So how do I smooth a PL function? Well, if it's a convex function, there are thousands of ways to do it. One is better than the other. But if it's a non-convex function, I'm not sure what's the preferred way to smooth non-convex function. So one way I know how to do it is just to take a convolution with some modifier. So and I look at this and this large sphere around it, and this is my map here. So this is my object. So what's going to happen is that let me just describe it. So over here, over the vertex, what I get is, so okay, this is my co-amoeba here. Let me see what's my co-amoeba is. Over this vertex, and this is the co-amoeba over this vertex, which is kind of the same thing in this case. So what's the fiber over the thing? So the fiber is actually going to be over this vertex. And the fiber over this vertex is going to be, let me see, this one. And what's going on in between the vertices, so this point somehow has to be connected to this point. And as I go along this edge, that point slowly sort of drifts towards this point. And this point sort of drifts toward this point. So the picture looks like this. So I'm actually, this is over here, this is here, and then this thing somehow connected. So maybe I'll draw another picture for the surfaces. Give an example for the surface. So this is as far as I can go with pictures. So if you have an edge, again in a triangulation, that corresponds to the face, to the two-dimensional face of the surface, something like this. Oops. And what's the sphere look like? So over kind of every vertex, the fiber is going to be, so this is tau, again, an edge. So this is a dual face to the tau, and the sphere are going to lie over it. So the picture would be, well, I'll just draw it. So this is the fiber here, this is the fiber here, this is the fiber here, it's the fiber there. And then somehow as I move along my surface, I kind of interpolate between this point and this point and this point and that point. So I have a name, I don't know if it's a good name, twisted coffin. That's what it is, what it looks like. Okay. All right, so now I'm going to define the morphisms. So what's a morphism? The morphisms are the intersection points of those things. Or of course, obviously, if the tau, yeah, and the name for this has actually been studied. I don't think it's studied enough. People study convex polytopes. Convex polytopes sort of do things to the convex PL functions. If we have a non-convex PL functions, then we have a non-convex polytope. So that's the so-called twisted polytope. I think the first appeared in Pukhlikov, Khovansky work in the 90s when they studied the cohomology of vector bundles on toric varieties. And so if you have an ample line bundle on a toric variety, that's very nice story that you have a H0 of that thing is the integral points in the corresponding convex polytope. If I have a non-ample line bundle, which corresponds to a non-convex function on a fan, then there is a parallel story that you can compute the cohomology of the line bundle as integral points in this twisted polytopes. So I'll draw some examples. Maybe I'll start with an example before giving a general definition. Maybe over here, coffin. goes away. So here are the basic. So you cannot have a non-convex thing with 3 rays. So on P1 on Pn, every bundle is either ample or sort of no sections, no cohomology, or like only the high one. So you either have a polytope or the polytope in a degree n in some sense. So it's not interesting. So the first interesting example, I guess, is F1. Let's see. So 1, 1, 0, 0. So this is a line bundle on F1. So how would you represent its cohomology? Well, you draw the thing. So you draw these 2 lines, and then you draw the lines which are hyperplanes which are orthogonal to the other 2 rays with the corresponding shifts by the values here. So, and then if you look at the, so this is my twisted polytope in some sense. So I think that this is a degree 1 and this is degree 0. So now you have for the convex function, you always have a degree 0 for your integral points. So in some sense, or if this was not 1, like I don't know, 5, for instance, and 5, then you would have some integral points there and some integral points there. This would represent a 0 cohomology. This would represent the first cohomology. There is a subtlety with a boundary actually. So for the 0 ones, you actually if it's an integral valued function lambda, then you would have to be careful whether to include the boundary points or not. If it's an ample one, then you include one. But if you know that, for instance, on Pn, if it's a minus ample, then you don't include the boundary points for the corresponding polytope. So here you include the boundary point, and here you do not include the boundary point. For us, it won't matter because our function is going to be never going to be integral. It's always going to be half integral. So we will not have this issue with the bound, whether to include or not boundary points. Maybe another example, another good example would be something like let me check my. Something like this. The value you want maybe like 2 minus 1, 2 minus 1, minus 1, 2. The boundary of this convex thing is always an immersed sphere. So again, so it has a sort of very many same features as a convex polytope. All right. So, but we define it as this polytope as actually as a full sort of complex. This is kind of a check complex which computes the cohomology of the line bundle. And of course, with usual differential, which is just the inclusion of the smaller cone into larger cones. All right, now the morphisms are, okay, this is a kind of complicated. If I have 2 objects like this, I'm trying to compute the intersection points. So when I compute the intersection point, this is what I came up with. So I take actually not just a single twisted polytope, but the whole bunch of them. So maybe I'll do this example here. So let me compute self-morphism for this one. So home of tau, tau lambda like this. So what do I do? Well, okay, this is my tau. I'm trying to, it's a tau with itself, so what I'm trying to represent, okay, so of course the morphisms is 0 if the tau and tau1 and tau2 don't intersect in some sense. So that means that they are not part of the same simplex. The only thing when they do intersect if they span a simplex. So in this case, the tau is itself, so they span the simplex tau, so delta is tau1 equals tau2. And what I'm trying to do, I'm trying to represent this delta, as a span of disjoint faces of it. So for instance, I can do, from tau1, I can take the empty one and tau2 to be the whole delta, tau1 to be one vertex, tau2 to be, so trying to write delta as a tau1 prime disjoint span. Well, how do I call it? Disjoint, well, I don't know, let's call it like this, tau prime 2. There are 4 ways to do it. So, and for each of the ways, I'm taking a particular function lambda. So if it was like this, so I have 4 twisted polytopes. 0, minus a half, minus a half, 3. Then I have minus a half, half, 0, 3. Then I have 0, 1 half, minus a half, and 3. And the last one is 1 half, 0, 3. So let's draw the twisted polytopes. Let's actually, well, okay, let's compute the not. Let's just write down the cohomology of it. So over here, if you think about this, what can I do? I can add, 1 half to everybody here, and then my twisted polytope is going to be from 1 half to, I guess, 3 halves here. Minus a half. Oh, yeah. 1 half minus 1 half. Okay. So this is the same thing as 1 half, 3 halves, 3 and a half, and 0, 0 here. So that brings me minus a half to 3 halves, 3 and a half. So that's 4 points here. 0, 1, 2, 3. If I modify this one, let me actually look at my notes. Minus a half, 3. So here I have 0, 1, and 2. Only 3 points. Here I have 1, 2, and 3. And here I have from 1 half to 2 halves, 2 and a half. So it's only 1 and 2. So now, if you think about it, this is indeed the if I take my original, remember, pair of pens, not pair of pens of this thing here. So I have my, for instance, the one object is like this, and the other object, that's the difference of the two, and the other one is the twisted thing, three times. So these two things, okay, so how many times this circle intersect this twisted circle? So this has two strings, and this has also 2 strings, but these 2 strings are kind of, if I'm trying to draw it like this, so these 2 strings are twisted as they go. So, and every string here intersect that string here in three times. So this is these 2 things and these 2 things. So one point here is kind of moved from this one. This is just a self-intersection of the circle. Anyway, this is a computation. And this is what the self-intersection points. Okay, so I probably will skip this. When is this a spherical object? It's actually interesting thing. So this is Gabe was very much interested in this thing with this, flops and things. So in this case, this is so if I have put a 0 here, then I only have a one-dimensional cohomology for the -1/2, -1/2, and 1/2 and 1/2. So if I have a 0 here and here, then this thing actually has no integral points inside. This is, this is actually, this function is actually linear, right? So -1/2. So if I sort of move it a little bit, this is a linear function. This represent a single point which is not integral. So this has no integral points. This has no integral points. This has one integral point with the degree 0, and this one integral point with degree 1. So this is so this represents the cohomology of the circle. But interesting case would be so in some sense this corresponds to this thing being flopped like this. If you look at at example, for instance, where it's not a circuit, for instance, like this, and if you try to draw the corresponding circle on a curve, right? So this is going to be something like this. So this is your circle. But if you draw this circle actually self-intersect. So this is not a spherical object, and you can compute its homes. It has a middle terms. All right. So I have 7 minutes, maybe something like that. All right. So we are mirror symmetry people. We try to prove mirror symmetries. All kinds of it. So let's look at the dual B side. It's not A side, so it's a B side. For this, the same data, namely this integral points, we can associate the toric variety and the Landau-Ginzburg model on it. And we try to do the computations over there. Yeah, by the way, I didn't, well, okay, this is just, we didn't finish, of course, we are very, very far from finishing the thing, but we believe this is a infinity thing. So we're still trying to define, this kind of holomorphic disks in this setting. But I believe it's possible. DG, this is a true DG side. We put all our integral points on level 1. So this is our thing here. And take the cone over it. This is a toric variety called Y. And okay, so this has a map to just a toric variety, which is a single, which is, C. And this map is called a superpotential, W. That's the Landau-Ginzburg model. And we try to do the computations there. Yeah, this is what I did. We try to do it in this Cox ring. namely, you take this homogeneous, ring of this toric variety, and a W is just a product of all the monomials. And we're trying to do we're trying to compute the graded matrix factorizations of this thing. So for every object, so I'm defining the matrix for factorization for every tau lambda in a usual way. And when we compute the Homs, we see that, well, at least we didn't compute it in general, but we did try several examples and it matches. So I guess it's a mirror symmetry. Well, in this very, very combinatorial kind of form. Of course, I mean, there is more to do, right? So this is a GG thing, so we need to do this homotopic contraction argument to compute the higher, m's for the A infinity things, but that's still work in progress. So far, we just computed the Homs, and I believe the product on Homs also is okay, but that's as far as we done so far. Okay, thank you.